So let's talk about partial differential equations. Now, what you have learned so far in calculus, in a Calc 1, which is required for this particular class, but you know you have not seen partial differential equations, but the principle of taking the first derivative would be the same, but we just maintain when you have multiple variables, you only maintain one variable and rest of them constant. So we're going to talk about that. I'll show you step by step. So let's start. All right. So let's say, for the sake of argument, we have an equation that you are more familiar with. Let's say PV equal to nRT. All right. So when you have PV equal to nRT, which is a gas law equation, but let's just assume that, let's say, let's even make that easier. Let's say N is equal to 1 mole. All right. So, so it's molar gas law. So let's make that into PV, right, equal to RT, just for the sake of simplicity. All right. Let's say, all right, assume, all right, for the time being, all right, for simplicity, all right. All right. So PV equal to RT, that's fine. So in this case, it's safe to say that P is a function, right? P is a function of, let's see, V is a variable, and T, all right? V and T. Of course, R is a constant. It's a gas law constant, right? So, but if you change a volume, the pressure would be affected. If you change temperature, the pressure will be affected, right? So in this case, so it's safe to say P is a function of V and T. Of course, if the number of mole changes, let's say, if you have gas combustion or reaction, number of mole of gas change or something, and then you can also add N as a variable. But we are just assuming it's 1 mole and it doesn't change, right? So in this case, all right, so this is because you can safely say that because P is equal to is a function of V and T, because you can say it's RT over V. All right, so far so good. All right, so in that case, all right, so if we have a variable, so we have two variables. So but let's say for the sake of simplicity, let's just keep one constant. So let's take a derivative, but we call it partial derivative, right? So let's take a partial derivative. Partial derivative, all right? So let's take, so d. Don't write this yet. Just watch this. All right, dp. All right, don't write this yet. dp over, let's say, with respect to, let's see. How about with respect to t. All right. So dp over dt. All right. Now notice that I use this symbol d as in like this d. All right, instead of d here. Right, this d right here is used for partial derivative, right? So partial derivative, all right, is d. This d right here is when you take the whole derivative. So it's you call it regular or normal, right? Normal, right, or whole, right? Derivative. We use this d symbol. But we distinguish when we use partial derivative by using this, squiggly d, all right? So, and then, with respect to t. But while we have two variables, v and t, so we call it while v is held constant. So this means while, all right, v is held constant. So in this case, all right, so dp over dt. So, if p is equal to RT over v. All right. So if that's the case, and then so t, so it's practically it's the same thing as r over v times t, right? So this part right here is constant because v is held constant. So what would it be? dp over dt. t to the first, right? So in this case, it's gonna be r over v, done, right? Because t, to the first, but minus 1 when you take a derivative, right? So do you see it? Somewhat, all right? So we call this partial derivative because, we are holding v constant. It's no different, right? No different from just taking the first derivative anyways, because you're holding the other variable constant. Easy peasy, all right? All right, how about you tell me, all right, dp, all right, over dv while t is held constant, all right? So what is it? Go ahead, do that, all right? Write it down, and I'll write it with you, all right? I'll write it with you, but don't wait, just go ahead, all right? So now, p is equal to rt over v, all right? So now v is the variable, t is constant. So in this case, you can call it as, all right? You can call it as, just for the sake of simplicity, you can just make rt times v to the minus first, all right? So and then we're going to treat v as a variable. So what would it be? Minus, all right, is equal to minus, all right, rt times v to the minus second, right? So far so good? Easy peasy, right? All right. So next, all right, so what should we do, all right? So second, so again, that's all it is. You're just taking first derivative while the other one is constant. The beauty of the partial derivative, all right, is that, you can take a second derivative, all right, as well as, the mixed variable derivative as well. And it doesn't matter which order you do it. I'll show you what I mean. In fact, all right, so let me write this down, what I just said, all right? The beauty, all right? Here's the beauty, all right? Beauty. Here, let's just write it down. Beauty, all right? Here, beauty, all right, of this, all right, of the partial derivative is that you can still take, all right, beautiful, right? Beauty of this is, you can take, all right, higher order derivatives, right? And also, it doesn't matter which order you do it first. If you have multiple variables, all right, while as long as you keep one, right, variable constant. I'll tell you what I mean. It's pretty, all right? So keep that in mind. Beauty of this, all right? All right? So let's do it here. So how about dp? So let's try again. dp, again, remember the variable, in this case, derivative, in this case, d is in squiggle d. So keep that in mind. It's partial derivative. So dp over dt, while v is held constant, what was it? It's r over v. All right, that's what you wrote earlier. All right. So let's say we take another derivative here. So second derivative. So how about d over dt? All right. All right. And then and then we do r over v. All right. So again, it's so it's in this case is equal to, all right, it's the same thing as, practically it's d over dt, dp over dt while v is held constant, and then while v is held constant, right, in this case, because t is the variable with respect to t, so v is held constant, right, because the other one is being held constant. In this case, v and v are both held constant. So in this case, d times d is what? D square, right? And then times p over dt times dt. So it's dt square, right? Oh, it looks like a second derivative, right? While v is held constant. Kind of cool, all right? So keep that in mind, all right? Of course, you can do it in different variables. So in this case, let's say I'll give you another example. Let's say, d over, how about dv, all right? On top of the, dp over dt, t while v is held constant. So in this case, the whole thing, it's dv. So the other one is, t is held constant. All right. So in this case, all right, so d times d is equal to d square p over dv times dt, dv times dt. Of course, dv means an infinitesimal change is made for volume, and infinitesimal change was made for temperature. So temperature is changing a little bit, volume is changing a little bit, and you can't no longer hold v and t constant, so these signs will diminish. All right. So, but it's still a second order derivative. All right, and we'll just leave it at that for the time being. All right. So in this case, these are the second derivative. All right. So in this case, this is what we call second, all right, derivative. With respect to, that's my abbreviation for with respect to v and t. All right, kind of cool. All right. So how about, let's do the other one. So how about I'll just use the space right here and see what happens. All right. So how about if I take a derivative, all right, over dt, all right, on and then let's see, dt, and then dp over dv while t is held constant. All right, and then while v is held constant. All right. So notice that dp over dv, dp over dt. So while the t is held constant here, v is held constant here. So keep that in mind. All right, here and here. All right. Now, so in this case, d times d makes it d square p, and then dt times dv. So dt times dv. Wait, it's the same answer, right? So in this case, although you took the first derivative of p with respect to v, with first derivative with respect to t, right? So the first derivative was done in a different variable, but if you take the second derivative of the other variable, it comes out the same, which means that's what I mean by it doesn't matter which order you take the derivative for the second derivative, all right, for multivariable derivatives. So keep that in mind, all right? That's the beauty, right? Of course, we don't use whole a lot of this application in our class, but just nice to remember, all right? So keep that in mind. Now that said, so let's move on to another, concept. So now knowing that, so let's say, remember, right? So remember, right? So now remember that. Remember, so go next, remember, right? Remember, the pressure is a function of volume and temperature, all right? And then, right, so if you want to make a change for P, you can either change by V or change by T, all right? So what the technique we use is called something called total differential. Total differential technique, all right? So watch it happen, all right? So if you want to, so let's say if, all right, so what I just said, if you want to make a infinitesimal change, right, change for P. So infinitesimal change meaning dP. Notice that I use the whole d, right, instead of partial d. You'll see why. If you want to make a P change, all right, then the whole change comes from the partial change. So in this case, dP over dV while t is held constant, all right? And then leave a space here. I'm going to put plus sign, leave a space here, and then I'm going to make another change, dP over dt while v is held constant, and leave a space here. But now, notice that, again, dP over dV. So if you change v, p will change, right? the rate of change is this derivative, all right? If you want to change p, the t, you can change that by doing t. But mathematically speaking, if you put, in this case, the whole v, dv, all right, whole d, this is a partial d, and I'm going to put dt here, all right? Whether it's partial d or whole d doesn't really matter in terms of like how you actually treat these numbers. But just write that down for the time being, all right? So again, so this way, mathematically speaking, dp doesn't have a denominator, so keep that in mind. This dp, the change of p comes from partial change, the rate of change, right? dp over dt, but dv and dv cancels out, so it's partial change p when you change v, right? While t is held constant, plus the partial change of p when you change t, of course dt and dt cancels out. So at the end, the total change of p comes from partial p change, all right, when you change v, and partial p change when you change t. That's called total differential, all right? So that's just a technique. So keep that in mind. So it's easy. You have two variables. You have dp over dv, while the other variable is held constant. You just write down dv and dv. And dt is in the denominator, so you just multiply times dt, and that adds up to the total change. Easy peasy, all right? So now, so keep that in mind. So let's do this, all right? So how about I'll erase this, all right? I'll leave this equation up for the time being, all right? How about I don't know, maybe volume might be a good, since we used volume, but let's say volume of a cylinder. So volume is a function of, radius and the height. How about that? So, and then of course from high school or something, you guys remember the, volume of a cylinder is like, I don't know, pi r square h or something, all right? Again, volume, you have two variables, r and h, that's fine, all right? But if you want to change the volume, so dV is equal to change, the whole volume change comes from each of the components. So if I do dV over, guess what, all right? In this case, dH, all right? While R is held constant, space here, plus, what do you think? dV partial change, the whole change comes from partial change when you change h, right? So dr, while h is held constant, of course, you have to multiply dh, so dh, right, so that they would cancel out, and times dr. Do you see it? Somewhat beautiful, right? dh and dh cancels out, so you have dv and dv, but the v change comes from when you change radius. The volume change happens when you change height, right? Because if you have a cylinder, something like this, right, you can either change the radius, right, that will change the volume, or if you change the height, that will change the volume, right? So you can change the volume of the cylinder in two ways. One is to change height, the other one is changing the radius. But the total change, right, dV, changing in volume, comes from either changing from the height, changing from the radius. Why do we care? All right, we will use this, all right? We will use this technique, all right? We will use this technique in error propagation. Right? Error propagation, you somewhat learned it in Chem 270 in analytical. All right? You will see that we'll use this technique in error propagation. All right? So, but again, what you learned in the sophomore level chemistry, right? We're gonna bring it up to the senior level. All right? So remember, you did like addition, subtraction kind of error propagation. We can be applied in any system. So we're going to talk about that in the next lecture. So keep that in mind and stay tuned. All right? right? So this mathematical technique is going to be used, all right? So remember this, all right? Easy. Whole change comes from the partial change plus the partial change with respective variables. That's all it is, all right? Good work, and I will see you in the next lecture.